All right, this video we're going to finish up the answers for the winter assignment, and just a few questions I'm going to go over. Again, this assignment is due on Friday, January the 8th, but I'm going to give you the weekend after that, so you have until the 11th of January to get this done. So let's go ahead and continue on. So we're on problem number 27 now, and we're going to pick up here with the Heisenberg uncertainty principle. This is simply a principle that says you can't know the velocity or the position of an electron at the same time. You can't know both of them at the same time. And it really gives the foundation of why we have to understand where an electron is in an atom based on probabilities, because we can't know its exact location. Anyway, what you see on your screen is the formula for this. It's not on the front of your assignment page or assignment sheet. So we'll go ahead and write this formula down. And you can just copy it down right there. So delta x is greater than or equal to Planck's constant over 4 pi times the mass of the electron, or whatever the object is, in this case, but it's an electron, times the change in velocity. So the change of velocity simply means the uncertainty. In this case, change in means the uncertainty of the velocity, and delta x means the uncertainty of the position, where it is. Okay, so we're going to go ahead and copy that down. Now we're going to go back to my sheet right here, and there it is. So I copied that down. So the first thing we did in the example is you have to calculate the uncertainty of the velocity. So it gives you a velocity here, and you're going to simply multiply it by this percentage. Okay, so the uncertainty delta V equals the measured velocity. That's what was measured. And the percent error, you can think of that as percent error, the percent that it's off. So you convert that to a decimal. Again, the simple way to do it is slide the decimal 2 places to the left. Or you could do 1.5 divided by 100. It'll give you the same answer. It's going to be 0.015. Okay, you can't use that number with the percent sign. You have to change it to a decimal. So go ahead and calculate that. And what we get is 1.14 times 10 to the okay, so we had to make that number bigger. We got to make this smaller, 10 to the 7th, and it's meters per second. All right, now we take this number and plug it in here for delta V. So this is going to give us uncertainty of the position is either greater than or equal to. It's at least the number we're going to come up here with here. Mass, be sure it's given in kilograms, not grams, and it is. It's the standard mass for an electron. Used a slightly different number, very slightly different number on an earlier problem. And then for delta V, we put in this number. And again, I'm not going to do the unit cancellation because it would require me to deconstruct what a joule is, and we're not going to do that. So I'm going to do the calculation. I'll write it up here on the top. I didn't leave a lot of space for this problem. Let's go ahead and do that. Okay, so then when we do this, and I recommend you do these problems this way, not try to put all the scientific notation into one calculation. It's too easy to make a single mistake doing that, and then everything's wrong. So you're going to take this number, 6.026, divide it by 4, divide it by pi, divide it by 9.11, divide it by 1.14. So remember, everything on the bottom, you don't multiply these down here. You could take this, multiply all these, and then take this number and divide it by whatever you came up with that multiplication. But the way I do it is I take this, divide by 4, divide by pi, divide by 9.11, divide by 1.14, and when I do that, I get this number. Times 10, and it's negative 34 minus negative 31. So be careful when you do the double negative, but you're adding 31 back. That gets you to negative 3. Now it's minus 7 because this is on the bottom. So negative 3 minus 7 is negative 10. And if you slide the decimal over 2 places, and it looks like we could use 3 significant figures here. So we slide the decimal over to here, and we're going to get 5.07. You made this number bigger, so you have to make this number smaller. Times 10 to the negative 12. And what are we asking for? Position. So that's the delta x. Okay, that equals the uncertainty. It says change in position. I know that's the symbol for change in position, but it's the uncertainty of the position is equal to that. All right. It's really more important you understand the concept. They're not going to ask you to crunch a number on this problem, but you should understand the concept. Okay, I'm going to talk you through the rest of them. I want you to put them in your own words. It's one of the reasons I don't write them down. They are in the notes. So what is the significance of the Schrodinger equation and the wave function? The significance of the Schrodinger equation is that it gives the equations, and you've never seen what they look like. You don't need to see them. It gives the equations that describe the orbitals, the shape of the orbitals. That the s orbitals are spherical shape, that the p orbitals have that dumbbell or potato shape, and that there's 3 of them, and that they each have 2 lobes to them. That the d orbitals, there's 5 different d orbitals, and it describes their shape. So that's the significance of Schrodinger's equation. It describes what do those shapes mean. They're probability areas. It's where there's a 90% chance that you'll find the electron inside of those shapes. So they show the probability, and that's what Schrodinger's equation does. It gives you these probabilities that describe those shapes of the orbitals. So go back and look at those shapes. In fact, I'm going to ask you to draw them here. So I want you to draw 1s, 2s, 3s. That's right out of the notes, right out of the video. So go do that. Sketch and label the 3 p orbitals. That doesn't mean the 3rd row necessarily. It could be any row, but the p orbitals, what they look like, and the 5 d orbitals. So I just want you to do a nice, fairly neat sketch of them. It doesn't have to be beautiful or great 3-dimension, but that's what Schrodinger's equation describes, is those shapes. So go back to the notes and find those. Okay, number 32. There are 18 columns in the periodic table, excluding helium. Which columns represent the s orbitals? So we'll just go over and look at the periodic table as we do this. And the s orbitals are the first 2 columns. The one with hydrogen, the one with beryllium. And as far as this is concerned, helium should be over here, but it's not. So those are the s orbitals. They can hold 2 electrons. Even as they get bigger and bigger, the 3s, the 4s, the 5s, they can still only hold 2 electrons in the s orbitals. All right, so that's the answer to that. Again, I'm just going to talk you through these. I want you to put these in your own words. Next question. Which columns represent the p orbitals? This is 32b. So we come over here, and this square over here, this block, it almost looks like a perfect square here. Over here, from boron to neon and down titanium over to radon, excuse me. That is the p orbital. Okay, you notice there's 6 elements there. There's 3 p orbitals, px, py, pz. Each one can hold 2 electrons, so that's 3 times 2 is 6 total. So that's the p. The next question is ask you which is the d. Those are the transition metals here. Okay. And finally, it's ask you which is the f orbitals, which we never really touched on other than just to talk about them. Those are these 2 rows down on the bottom. The first one is called the lanthanide series, under element named after, because they come after element number, it comes after element number 57, lanthanum. And the bottom row here, the very bottom one, is called the actinium, or the actinide series, because it comes after actinium right there. So you can see that heavy line right there. So that's, again, another reason why the periodic table is shaped the way it is. It tells you which parts of the periodic table correspond to which orbitals. All right, let's go back to the next question. So we did A, B, C, and D there. I want you to just write those out. What is the Aufbau principle? It simply says that the electrons are placed in levels from lowest energy up to highest energy. And that is this, what we drew earlier. Okay, you start with 1s, 2 electrons go there, then 2 electrons into 2s, and then ultimately you fill up the 2p orbital, and then you go to 3s. So they're going up to higher and higher energy. That's called the Aufbau principle. What is Hund's rule? Hund's rule says that electrons space out so as to, or spread out so as to maximize their spin. That's the technical jargon term for it. But what it means is you put, in the p orbital, for example, you put up arrows in the px, the py, the pz, and then you go back and put down arrows in the px, py, pz. You'll see that in just a minute. We're about to do several of those, and that rule will be clearer. But it says electrons spread themselves out. Okay, so you go into a movie theater and a bunch of people you don't know, you don't sit next to anybody, and the next person doesn't sit next to anybody, but finally the theater starts to fill up, and then people have to sit next to each other. And that's what Hund's rule is saying about electrons. Finally, the Pauli exclusion principle says that in any one subshell, if you have 2 electrons, one of them has to have a plus 1/2 spin, and one of them has to have a negative 1/2 spin. Don't worry about what the number 1/2 means. It just means plus and minus. They have to have opposite spins. Normally, electrons want to repel each other because they're both negative, but if they have opposite spins, they're at least able to live together in the same subshell without pushing each other apart. And so it just says electrons must have opposite spin. So again, just use that phrase, opposite spin, plus 1/2, minus 1/2. Okay, so I want you to put all of those in your own words. Now we're going to do a few of the Aufbau, using Aufbau, Hund's rule, and Pauli exclusion principle. Okay, just to conclude this assignment, I gave you a series of problems to go ahead and practice Aufbau, Hund's rule, and Pauli exclusion principle, and then to write the electron configuration and the condensed electron configuration. Okay, so the first one is boron. So let's go look at the periodic table. And boron, we know, is in the second row, and it's in the p orbital. That one of its electrons, it has its 1 electron into the p subshell. So the way we're going to draw that is going to look like this. And you should get in the habit of drawing them in the proper sequence. Don't just fill in a bunch of arrows to the point where you want to be. So we're going to do it in the proper sequence. So the 1s orbital has an up arrow and a down arrow. Okay, usually draw them as little half arrows like that, up and down. The 2s orbital has an up arrow and a down arrow. Again, we're dealing with boron. And then the 2p had 1 electron. It's an up arrow, and that's it. That was boron. So that, you have hydrogen, helium, lithium, beryllium, and then boron. Okay, so that's the first element. It's the first electron or first element in the 2p orbital. So that's it. That's all you had to draw for that. Now the electron configuration is 1s, and there's 2 electrons in the 1s, so it's 1s2. Be careful, my s's look like 5 sometimes, but it's an s. These are all s's. There's no 5s here. Okay, then you got 2s2. Try to make them a little bit better. And then you have 2p1. When you're writing this configuration, you don't pay attention to x, y, z. It's just in the p orbital. So it's 2p, and there's 1 electron. These superscripts, they're not exponents, they're superscripts, are telling you how many electrons are in that orbital. Okay, the condensed electron configuration, what it does is it goes back to the previous line. It finds the element you're looking for, in this case boron. It goes back to the previous line, and instead of writing everything, you just start with the noble gas that is in the previous line. So in this case, we start with helium, because boron is in the second row. So helium is the noble gas in the row before it, so that's He. So you come back here, and you, in a square bracket, you always use square brackets to do this, you write He. Now these two represent helium right here. That's helium. 1s2, that's the end of the first row, that's helium. Then you just write the rest of it after that noble gas. So it's 2s2 and 2p1. 1. Now you say that isn't any shorter than that, but it will be when we get to elements further down the periodic table. Okay, so that completes that problem. Let's go and do aluminum. So aluminum is here in the third row. It's right below boron. So we're going to write it the same way. We're going to have a 1s2. Then you have the 2s2 right here with lithium beryllium. Now the entire p orbital is filled up. That's 2p6 because all 6 of those are filled up. And then you have to come down to 3s2. That's sodium and magnesium. And then aluminum is 1 electron into the 3p orbital. All right, so we're going to go ahead and draw that. Okay, so, and you can memorize your elements a little bit, practice that by just saying the element. This is hydrogen, helium, lithium, beryllium. Now watch how I do the 2p. I want you to do these in order so you get used to the idea. Hund's rule says that you have an up arrow. Now what do you have next? A down arrow? No. You have another up arrow here, and you have another up arrow here. So that's Hund's rule, that they spread out. That's what we talked about, maximizing their spin. That's just the phrase they use. They spread out. That's really what it's saying that they do. So now you have those 3. Now you have to start pairing them up. So you put a down arrow, down arrow, down arrow. The fact that it's up arrow, down arrow in each of these is the Pauli exclusion principle. You can't have 2 up arrows. You can't have 2 electrons with the same spin. Now that we've gotten to the end of the p orbital, the end of the p orbital always represents, with the exception of the 1s orbital, which is helium, the end of any p orbital represents a noble gas. In this case, it would be neon. Okay, now we keep going. To aluminum, you have to go through the 3s orbital, up arrow, down arrow, and then 1 electron into the 3p orbital. Again, let's look at that, and that's where we stop. So let's look at that here. So there's aluminum. It's 1 electron, it's 1 element into the 3p orbital. So everything that comes before it has to be filled. But I want you to practice filling them in the proper order, and then you get a 3p1 for aluminum there. Okay, so that's what that would look like. Now let's go ahead and write the electron configuration. It's 1s2 right there, then it's 2s2. Now it's 2p6. So you're in the second row, the p orbital, and all 6 electrons are placed there. Now we keep going up to 3s. And there's 2 electrons in the 3s. And now we have that one last electron to get us to aluminum, and that's 3p1. All right. Now we said that the end of a p orbital is a new noble gas. And if we come over here, there it is. So if you're at the end of the second row, you're into the end of the 2p is neon. So we're going to start with neon for our condensed electron configuration. So we come back here and we realize that this, if you take all these together, that's the electron configuration for neon. So we're just going to start with neon. Okay, and then we're going to take everything else that's not part of this, which is the neon configuration. So it's 3s2, 3p1. Okay, and that's it. That's how you do that. Okay, now we're going to move on to copper. So let's look at the periodic table. And where's copper? It's right here. It's number 29. It's the second to last transition metal in this row right here, next to zinc. Zinc would be the last transition metal. Now, if you read the notes carefully, at the bottom of page 12 and 13, there was an exception to how you do the Aufbau. So far, it's been pretty easy. You just go row, 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 and add electrons. Now there's going to be a little twist here. So I'm going to do it the way that you would think it should have been done based on what you just did on this first 2 problems. And then we're going to make the correction that we need to correct, and we're going to explain why. Okay? So here we go. So copper is going to be hydrogen, helium, 1s2, lithium, beryllium, 2s2, and so on. Okay, so let's go ahead and do that. So copper is going to be the 9th element over in the 3d orbital. Be sure you understand that that's the 3d orbital. It's in the 4th row, but it belongs to the 3rd row, and it's the 3d orbital. So let's go ahead and do that. So up arrow, down arrow in the 1s. You have to fill up everything all the way up to there, but do it in the proper sequence. So there's 2s, and then you have up arrow, up arrow, up arrow. That's what I mean by proper sequence. Don't do up, down, up, down, up, down. Remember, this is Hund's rule. And then down arrow, down arrow, down arrow. The fact that up and down have to be paired up like that is Pauli exclusion principle. Then we go up to 3s, up arrow, down arrow. Then 3p, up arrow, up arrow, up arrow, down, down, down. And now we're up to 4s. We fill that. Now, I'm going to do one of these lightly, and you'll see why. See if you remember, if you read the notes, how would we do copper? Copper is going to be the 9th element in the 3D. So we're going to do an up and a down, and then we're going to do up, up. Okay, there's 9 electrons in that d orbital. Copper's the 9th element over in the d orbital. It's the 11th element over in the 3rd row, in the 4th row rather, but it's the 9th element over in the d orbital. So here we go. So now we do down, 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 and we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're done. Okay, it looks like we're done, but there's a twist, and you just understand this rule that orbitals prefer to either be filled or half filled. So if you look right here, copper is only 1 electron away from having a filled d orbital. Okay, so what it can do and what it does in this case, anything that's in the second to last element in the transition metals, let's go back and look at what those would be. Those would be copper, silver, and gold in each of their respective rows right there. They're the second to the last transition metal, not the entire periodic table, but just the transition metals. They're second to last. So what they will do is this. Those 3 elements would do this. They're going to borrow an electron from the s orbital. In this case, copper's case, it's the 4s orbital. So we're going to erase that line right there. We erase that electron, and now we're going to place it over here. Alright, so now copper has a half-filled 4s orbital and a completely filled 3d orbital. So orbitals prefer to be either filled or half-filled, so now it has a filled and a half-filled orbital. Whereas before it had a filled 4s, but not a filled 3d. So this is the configuration, okay? It's just kind of oddball, but you just kind of learn it. There's not a lot of these exceptions, but this is one that you should know. So let's go ahead and write the electron configuration. It's 1s2. Again, the 1s has 2 electrons in it. Everything up there until you get to the end is going to be filled. So 2s2, then 2p6, and then 3s2, and then 3p6, okay, and then 3p6, then 4s1. So you just took that electron away. So now it's just 1 electron there. And then 3d, you go backwards, and it has all 10 electrons there. Now there are some books that will show the 3d. They'll do it in just proper number order. The 3d will come before the 4s. I don't do it that way because I want you to follow the periodic table, and your book doesn't do it that way either. Follow the periodic table in terms of the orders. The 4s comes before the 3d orbital on the periodic table as you simply go line by line by line down the periodic table. Okay, where is our biggest filled p orbital? It's right here. So that's going to be a noble gas. So I'm going to just put a big brace across that. And what noble gas is that? The noble gas at the end of the 3rd row, just look on your periodic table, is argon. Okay, so what we're going to do is take all this and simply represent it as argon. And then we're going to take the rest of it and put it out here. Okay, and that's everything. All right, go ahead and do strontium. See if you can do that on your own. Okay, so let's go down here and let's find it on the periodic table. So strontium's right here. It's the second element over in the 5th row. Okay, so we're going to fill everything up before that. So let's go ahead and do that. Hopefully this is becoming kind of easy. So it's in the 5s orbital. What does that tell you? It means everything up until here is going to be, including this, is going to be filled. But still practice doing it in order, okay? Up, down, up, down, up, 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 down, down, down. Okay, no tricks here. That's just the way it looks right there, just like that. Okay, so let's write it out. Okay, it's a lot of writing. But what's the largest p orbital that's filled? It's this one right here. And that's going to be krypton. So all of this can be represented as this, just krypton. And then all you have left over to write is just that. So that's really where the condensed electron configuration comes in handy. Okay, let's take a look at, see what else we got here. That's it. That does it. Okay, just be sure you know that. It's not a hard concept, and just know that that one exception. There are some strange exceptions when you get into the F orbital. We're not going to deal with that now. Maybe we'll talk about that in the spring for those of you that really want to pursue the AP exam. Okay, that's it. It's a long assignment. I'm giving you really an extra week on it because I got this up late due to circumstances I couldn't control and over the break. But go ahead and get it done. It is a tested concept on the AP, everything that's in this unit. Okay, so I look forward to seeing you at school again on Monday, and have a great rest of your holiday.